in the previous video, we discussed 3 different models of different objects on the vertices of a honeycomb. We discussed the Haldane, the model, the P-wave superconductivity, and the Kitaev spin liquid. We discussed the gapped A phase, the gapless B phase, and when we introduced next nearest neighbor interactions, the chiral phases, chiral Chern insulator, chiral P-wave superconductor, and chiral spin liquid. In this video, we want to concentrate on a different subject which is related to these materials. This is the degeneracy on a torus. So when we put these models, these honeycomb models on a torus, the question is, what is the degeneracy of the ground state of the system? So why it is important to discuss the degeneracy on a torus? First of all, there is an issue of classification. Topologically ordered state is a state of matter whose ground state is degenerate on a torus. So this is a definition of a topologically ordered state. The important thing that we have to take into consideration and to think about is that this degeneracy does not depend on details or on symmetry. We know examples for degeneracies. For example, if we have an atom, due to the spherical symmetric structure of the atoms, there are certain degeneracies in the atomic levels. When we break this symmetry, this degeneracy is lifted. This is not the case in the topologically ordered matter. The degeneracy does not depend on the details. If we introduce disorder in the system, the degeneracy will remain. It will not be lifted. Another thing which is important to know about this topologically ordered state is that local measurements cannot distinguish between degenerate ground states. So we have 2 ground states which are different in certain properties, but in order to distinguish between them, we have to perform a non-local measurement. This is again different from the situation which we know, for example, from a ferromagnet. Ferromagnet, all the spins in the system, in a ferromagnet, all the spins in the system will point in the same direction, and there are degenerate states depending on the direction of the spins. If we measure one spin among all these spins, which is local, we already know in which direction the whole ferromagnet points. This is not the situation in the topologically ordered case. We cannot distinguish between the degenerate ground states by a local measurement. Now, there is another property of the topologically ordered state, which is important. There are emergent internal quasiparticles. We met already some of them in the fractional quantum Hall case or in the Kitaev spin liquid phase, where there were internal vortices in the system. The last thing which I want to say is that the topologically ordered case, unlike other cases, is an interesting many-body problem. So that means that I cannot write the problem in a quadratic form and solve it. We have to use different different methods in order to understand how this system behaves. Let's discuss the differences between P-wave superconductor and the spin liquid case. So P-wave superconductor in the mean field approximation that we discussed is a quadratic problem. This is certainly not a topologically ordered case it's not a quadratic problem. External vortices in the case of a P-wave superconductor give rise to Majorana zero modes and degeneracy. We discussed that a lot in this course. If we have 2 Majorana zero modes, they together form a state which can be empty or full. Now, these states are topologically protected. Local measurement, if I measure the charge or try to measure the states of the system in 1 Majorana, I will not be able to distinguish between an empty or full state. I have to perform a non-local measurement in order to distinguish between the cases. So in this sense, it's topologically protected. However, the state P-wave superconductor there is no degeneracy on a torus. If we have n vortex lines in the system, if I create a vortex into the torus system, then we will have a degeneracy which is exponential in the number of vortex lines. So this is the case of a P-wave superconductor. In the case of a chiral spin liquid, the situation is different. First of all, it's a many-body problem. It's non-quadratic. The spin models are not exactly you have to use different methods, not simply diagonalize a quadratic Hamiltonian. The degeneracy on a torus is protected without any external defects in the form of vortices. In the non-abelian case, this is, for example, the spin-liquid case that we discussed in the Kitaev honeycomb model, there is additional degeneracy when we have introduced internal excitation, or when there are internal excitations in the system. So the emphasis on the differences between P-wave superconductor and the chiral spin liquid is the fact that in the chiral spin liquid's case, the degeneracy is due to internal particles that are a part of the system. In the case of a P-wave superconductor in the mean field approximation, we have to introduce this defect by externally by adding, for example, vortices in the system. So I want to emphasize one caveat that is related to this problem. The difference between the P-wave superconductor and the chiral spin liquid were on the level of the mean field approximation. In real, experimentally available maybe P-wave superconductor, there may be a phased Goldstone mode. Maybe there is this mode that makes the superconductor ungapped. There are also anti-vortex excitations in the system, but all that go beyond the quadratic mean field P-wave superconductor, which we discussed in this course. And now we go back to the case of Kitaev spin liquid model, and what I want to show you is how by internal excitation of the system we form a state which is equivalent to insertion of a vortex line, but it's done by internal excitations of the system. So due to the gauge field fluctuation, we may change one of the bonds and we create a vortex-anti-vortex excitation. In this loop we will have an odd number of minus signs which give rise to zero modes. These are so-called sigma particles of the Kitaev spin liquid model. And what I want to show that by manipulating this internal excitation, we get a state which is equivalent to insertion of a vortex line into the torus. So imagine that this vortex is this circle, this blue circle is a vortex loop, and we insert these vortex loops into the torus. So how it's done by internal excitation? We start from two sigma particles. By changing by the gauge fluctuations, we change the sign of one of the bonds, and we can move that. Now you see that in this hexagon we have one bond with an opposite sign, and in this hexagon we'll have two bonds with opposite signs, so we didn't change, so that middle hexagon will not have a vortex, will not have a sigma particle. Now we can move this sigma particle more, and the nice thing is that we always have only two hexagons with odd number of inverted bonds. As we move them further on, we can complete a circle around the torus until the two vortices, the two sigma particles, meet each other and annihilate each other. So you see that in this way, by internal excitation, we form a vortex loop in the torus. So this is a situation which is of course different from the original problem, because we have this line of minus signs, but each hexagon here we still have, in this case, we'll have the same even number of the multiplication of the sign of all the bonds will always be plus. So this vortex in the y direction will change the boundary condition to trajectories in the x direction that must cross one bond which is negative. So without this vortex line, without this flux, the boundary condition will be such that we have a half integer quantization, and when we add the flux, we go from half integer to integer quantization. This will be the odd case, this will be the even case. Now it's important to notice and to understand that due to the energy gap in the lattice model, the difference between the ground state energies with even or odd boundary condition is exponentially small. Now it takes a bit to prove that, and I leave that to you as an exercise to show that the difference in the energy is exponentially small in the size of the trajectories m, the size of the torus m. So let's see how, what is the difference between the different ground states. So we think there are possibly 4 possible ground states, right? Without any flux lines, with a flux loop in the y direction, with a flux loop in the x direction, and with 2 loops, one in the y direction and one in the x direction. Now, I don't discuss 2 loops, a situation where one may ask why not to put 2 loops in the x direction, and that's of course clear that then we will cause 2 bonds with negative sign and we will not change the boundary condition. So 2 loops are equivalent to nothing. So we expect to have 4 equivalent ground states. But do we really have 4? Let's examine that situation very carefully. So here I choose m equal to 4 for the illustration of the problem. So in the odd case, that's a situation without any fluxes. The boundary conditions are such that kx is half integer, and also ky is half integer. So I put these white circles here to show that both kx and ky are half integers of n. If we introduce one flux loop, we will get to the even-odd situation when kx is an integer and ky is half integer. That will put, you see that here kx is an integer multiplier of 2 pi over 4, and ky is half integer of that. In the odd-even case, the situation is opposite. We'll have kx is half integer and ky is an integer. This is the odd-even case. And the last case is the even-even situation when both, we change the boundary conditions for both the x direction and the y direction, and we will have just integer numbers. So this is a summary of all possible boundary conditions with even or odd boundary conditions, and with or without fluxes. So all of them seems correct. They all, as I told you, they all will all have the same ground state energy, but there is one state here which is very special, and this is the even-even case. Only the even-even case will have the zero case. That means that kx is equal to ky is equal to 0. K is simply 0. Now, I remind you that we discussed the p-wave superconductor, so the pairing term will have this form. Now, the fact that we have a state with k equal to 0 means that one fermion is unpaired, so that the ground state parity is different. So that 2 loops state does not belong to the same parity sector of the all ground states. So the degeneracy is not 4 because this belongs to a different sector, and it will be, we will have 3 degenerate states in the case of Kitaev honeycomb model on a torus. Now, so to summarize, p-wave superconductor has no ground state degeneracy on a torus, and the Kitaev spin model in the gapped phase, the B phase, has 3-fold degenerate ground state. And another important thing is that in contrast to the p-wave superconductor, the vortex excitations are dynamical due to the Z2 gauge field fluctuation. So these are internal excitation and not introduced by external vortices. And now I pass on the torch to Adi.
So thank you, Yuval, for the first part. What I'm going to do in this part of the video is to discuss the relation between the degeneracy of the ground state on a torus that comes together with topological order and the fractionalized quasi-particles and quasi-holes that come together with topological order as well. And naturally, the first case to think about is the nu equals 1/3 fractional quantum Hall state. That was the first topologically ordered states we saw in this course in the chapter about the fractional quantum Hall effect. Now, we saw there that the quantization of the Hall conductivity to a fractional value forces us to realize that there will be quasi-particles and quasi-holes with fractional charges. And we also saw that those fractionally charged quasi-particles and quasi-holes will follow an unconventional type of quantum statistics, fractional statistics. We even sketched the calculation of these fractional statistics. I'm not going to repeat the outline of the calculation, but just to remind you of what the process is. So in this process, we have two quasi-holes, and we make one of them go around another full winding. So you see that now as a function of time in the z direction, in the up direction. You can also see it in a side view or in a top view, just as one quasi-hole going around another. So when we carry out such a winding, if we do it adiabatically and we start in a ground state, we will end up in the ground state. But ground state multiplied by a phase factor. And in the nu equals 1/3 case, we said the phase factor is non-trivial. Now, if we start from nu equals 1, for nu equals 1, non-topologically ordered state, no fractional quasiparticles, the quasi-holes and quasi-electrons are just electrons, fermions. And therefore, when one goes around the other, it accumulates a phase factor of 2 pi. And we can understand these 2 pi because a full winding is just two processes of exchange. One exchange this way and one exchange that way. And one exchange this way and one exchange that way. And when we exchange fermions, we get a phase factor of pi. We express this phase factor of pi by looking at the anti-commutation relations of the electronic creation operator at two different points, and then interchanging these 2 points. In principle, it would be nice to have a similar relation for the 1/3 quasiparticles, but that cannot happen. And it cannot happen because when we say we interchange two positions, we do not specify whether we interchange them this way or that way. And therefore, we cannot write commutation relations of the type we wrote for the electrons for fractionally charged quasiparticles. Instead, what we can do is we can think about the torus and look at the commutation relations between loop operators. So as we saw in the presentation of the toric code by Erez here in this chapter, there may be loop operators on the torus that go like that and loop operators that go like that. In his case, there were operators associated with the electric, magnetic, and product quasiparticles. In this case, there will be loop operators related to the 1/3 and minus 1/3 quasiparticles. In any case, there will be loop operators, and those operators will tell us a lot, just as they did in the toric code. So let's see what they tell us. So the properties of those loop operators are going to be similar to those we saw for the toric code. They commute with the Hamiltonian. Both the operators that go in this direction, the x's, and those that go in this direction, the y's, they are going to commute with the Hamiltonian. Not only that, the various x's commute with one another, and the various y's commute with one another. But the x's and the y's do not commute. xj prime times yj will be related to yj times xj prime by a phase factor. And the phase factor is not a plus minus 1. It's a non-trivial phase factor. Now, this combination of relations immediately tell us that the ground state must be degenerate. Why? Because imagine that we took a ground state, psi, and we took one that is an eigenstate both of x and of y, then x multiplied by psi will give us some eigenvalue times psi. And frankly, I don't care what this eigenvalue is, so I won't even write it. Now, I take this state, and now instead of psi, I multiply psi by y. Then I'm going to get a different state, y times psi. To the extent to which it is different will become clear in a second. This is an eigenstate of the Hamiltonian as well, because if I operate h on y times psi, h and y commute, so I'm going to get the same energy that psi got. This and this are both eigenstates of the Hamiltonian. But now if I operate x on y times psi, since commuting these two involves a phase factor, I'm going to get a different eigenvalue of x for y times psi as compared to the one I got for psi. and since those two states have different eigenvalues for x, there are two orthogonal states. So there are two orthogonal states, psi and y times psi, that have the same energy. So the ground state is degenerate. Now I can repeat that and do y squared. And I can do that as many times as I want until I find that I got back to the original state or to the original eigenvalue of x. In this case, it will take 3 times. So I know that I have a threefold degeneracy, or at least a threefold degeneracy of the ground state. And I know in this case, I expected that because I have one quasi-hole of charge 1/3, quasi-particle of charge 1/3, one quasi-hole of charge minus 1/3, and a trivial particle which is the full electron. So 3 types of quasi-particles. So you see, threefold degeneracy of the ground state on a torus, 3 types of quasi-particles. And you see also that I used here in this case the y's to generate different ground states and the x's to measure which ground state I am on. I could have done it the other way. This would be just a rearrangement of the ground states. But I can always choose one loop direction to go from one ground state to another, and the other loop direction to measure which ground state I'm in. For example, I could do the same thing on another type of a topologically ordered state that we just had a long discussion of with Yuval. And this is the chiral spin liquid, the gapped phase of the chiral spin liquid that comes out of the Honeycomb model, spin model that we discussed earlier. So in this model, there are 3 different ground states, and they are characterized by 1, psi, and sigma as the names of the quasi-particle they correspond to. We saw the threefold degeneracy emerging from the physics of the P-wave superconductor and from the fact that you don't have 4 degenerate ground states because one natural candidate for such a ground state turned out to have the wrong fermion parity. Again, we can have the 3 different ground states generated by loop operators in this direction and measured by loop operators in the other direction. But the fact that one combination doesn't have the right fermion parity is expressed by the fact that the product of the loop operator associated with the sigma or vortex particle and the X operator associated again with the sigma or vortex particle, this product turns out to take the system out of the ground state manifold, and therefore is not useful for a measurement of which state we're in. But you see out of this table that by having these 2 operators, X sigma and X psi, you can identify what ground state you're in by applying them on each of the 3 ground states. So this is a second example. And the third example I'd like to discuss in this part of the video is the nu equals 5 half state. It's the first non-abelian state we talked about in this course. The nu equals 5 halves. So let me remind you what we said about it. We had a video about that in the first chapter. What we said, using these composite fermion mappings of fractional quantum Hall states to states at weaker fields, and in this case to a state at 0 field, we said that the nu equals 5 half state is equivalent to a 2-dimensional class D superconductor of composite fermions. And a class D superconductor has a Z classification. It has a topological invariant that can take any integer value. And if that integer value is odd, then the superconductor carries vortices with 0 modes at their cores. And we saw when we discussed that the smallest charge quasi-particle is exactly a vortex. It carries a charge of E over 4, and it carries a zero mode in the non-abelian case, which is the case we'd like to talk about. So it carries a zero mode. Now, in such a state, there will be, I will argue now, 6 types of quasi-particles. The first one, as we just said, is the single quarter charge quasi-particle, which carries a zero mode. So it's basically a vortex with a zero mode. If you bring 2 of those together, you'll get a total charge of E over 2, of course. But you'll also get what happens when you bring together 2 zero modes. You get out of those 2 zero modes a fermionic degree of freedom, which can be either full or empty. So we'll get 2 types of E over 2 quasi-particles. One with the fermionic degree of freedom being full and one with empty. As we now bring a third E over 4 quasi-particle, we'll get a 3/4 charge quasi-particle, and the zero mode will come back again. Because when you combine together 3 zero modes, you get 1. Then as we bring the last, in the last step, if we bring 4 charge quasi-particles, we'll get a charge E quasi-particles. Now, we'll get 2 of them. One of them is definitely the electron. And that's the one that has a fermion in it, because the electron is a fermion. But the other one will be charge E quasi-particle that's not the electron. So altogether you can draw this in a diagram, as we do here, where this axis is the charge. 0 here, E over 4, E over 2, 3 over 4, and electron charge. And that axis is the topological degree of freedom, is the state of the topological degree of freedom that the quasi-particle carries. So, you know, a quarter charge quasi-particle, we said, carries a zero mode. And that line is the line of the quasi-particle that carries zero modes. Those 2 lines are the lines of quasi-particles that carry a fermionic degree of freedom, and which may be either empty or full. So altogether, 1, 2, 3, 4, 5, and the 6th one is the same as the original one. So 6 quasi-particles altogether. So to summarize, we looked at an evolution process, if you want, where we start from a very simple tight binding model of electrons on a lattice, and we have just a quadratic Hamiltonian of fermions. Charge is conserved, basically, tight binding, non-interacting 2-dimensional model. And we saw that it can give rise to interesting phases, to a trivial insulator or to a Chern insulator. Those 2 are the gapped phases. Then we made it slightly more complicated by replacing the electrons by Majorana fermions. So, well, once you have Majorana fermions, it means you don't conserve charge anymore, and it means you went from the realm of Bloch bands to the realm of superconductors. And in this particular case, you have 2 phases. The trivial insulator became a trivial pure-wave superconductor, and the topological Chern insulator became a chiral p-wave superconductor. But it's still a quadratic Hamiltonian, no topological order, no ground state degeneracy on a torus. There is a ground state degeneracy associated with vortices, but vortices are extrinsic excitations that we need to put in. Then we went on to the next step in the evolution, that's the spins model, the spin hexagonal model, where there are no charges, so obviously they are conserved. But there are spin-spin interactions. It's not a quadratic Hamiltonian anymore, and it has analogous phases. The analog of the trivial insulator and the p-wave at the trivial state is the abelian toric code phase, and the analog of the other 2 here is the chiral non-abelian spin liquid. Now we have a topologically ordered state. And if it's abelian, as Erez showed to you, the ground state degeneracy on a torus is 4. And if it's non-abelian, the ground state degeneracy is only 3. But it's a topologically ordered state. And the last step that we just introduced now is the nucleus 5/2. Now we have fermions. Their charge is conserved. And they may form either abelian states or non-abelian states. And in the non-abelian case, there is a ground state degeneracy of 6, with the charge being a multiple of quarter charge. So this summarizes our discussion of topologically ordered states, which we were able to base partly on exactly solvable models and partly on approximation schemes, such as composite fermion theory. That discussion exposed us to the world of ground state degeneracies on a torus, of fractional statistics, of fractional quantum numbers, of abelian statistics, non-abelian statistics, a world of great richness.